Hey everyone, welcome back to another video of mine, where today we're going to be solving Leetcode problem 79 titled Word Search. So we're given an n by n grid of characters board in a string word, and we have to return true or false, basically a Boolean value, if word actually exists in the grid or board input. So the word can be constructed from letters of sequentially adjacent cells, or basically in other words, 4 directionally adjacent cells, where adjacent cells are horizontally or vertically neighboring. And the same cell may not be used more than once. So in example 1, we have an input grid of a 3x4 board to be A, B, C, E, S, F, C, S, and A, D, E, E. And our word input is going to be A, B, C, C, E, D. And we'd actually output true because they have basically highlighted the path that we can actually take to use 4 directionally adjacent cells to form every single corresponding or map every single corresponding element or word that actually forms the input word to be A, B, C, C, E, D. And let me actually zoom in for you guys so you guys can see that a little bit better. And so we'd output true because we can actually form that word using adjacent cells in our input board. In example 2, we have a board with the same dimensions, but our word is changed to C. And we'd still output true because they've highlighted the path where we can actually use 4 directionally adjacent cells to actually form the word C. And in example 3, we have a board to be another 3x4 grid of A, B, C, E, S, F, C, S, and A, D, E, E. But in this case, our word is going to be A, B, C, B, which we cannot actually form using only 4 directionally adjacent cells, and so we output false. You guys can feel free to pause the video and try to brute force any path or any cells that are connected that actually form the word. But note that diagonally connected cells are not considered to be 4 directionally or sequentially adjacent cells if they're diagonally touching, and so they would be considered adjacent in this case, or sequentially adjacent, and so we cannot use A, B, C, D like this to actually form A, B, C, D word. So I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll tell you guys how I would optimally solve this problem in a bit. Okay, to actually explain the algorithm and give you guys basically a rundown of how this is actually going to work, we're basically going to start by iterating through the board, starting from each cell. And if a cell matches the first character of the word, we will attempt to explore all the four directions that are basically 4 directionally adjacent to this current cell, up, down, left, and right, therefore, to find the next character. And if we successfully find all the characters, we'll return true. Otherwise, we'll backtrack and we'll basically reset the state of the board before moving on to the next iteration. And we'll basically be using a backtracking function or algorithm to explore the board recursively. And for our variables, we'll have, of course, the board and target words input. We'll have the current position, basically the row and column index or cell value. And we'll have the index of the current character in the word that we're looking at for one specific iteration or one specific search of our input board. And for the data structures, we're going to be using a visited list where we basically modify the board temporarily to mark cells as visited in corresponding searches. So with that problem statement and explanation of the code out of the way, let's actually go ahead and dive straight into the code itself. So let's actually store the number of rows and columns in our input board in two variables that we can easily access later on. And I'm going to just call that and define that to be self.rows using the self keyword in Python, basically the object-oriented programming keyword in Python, and self.columns. And I want to set that equal to length of the grid and length of the grid at index 0. And essentially what this is doing is that we'll basically store the number of rows and columns of the board in the self.rows and self.columns variables respectively to actually easily access them later, where the length of the board gives us the number of rows and the length of the board at index 0 gives us the number of columns. Now we'll actually use a nested loop to iterate through each cell of the board, and we'll do this like so. We'll basically say I'll just call this row as my iterator for this for loop. I'll say for row in the range of self.rows, or the number of rows present in my input board. And I'll call this column as my iterator in the range of the self.columns, or the number of columns present in my input board. Now I have to basically check for a backtracking function that I'll basically eventually define to check if the current path is actually true. and I'll say if self.backtrack. And essentially, when I actually call self dot a specific function name, I'm basically recursively calling that function in Python, where self is the object-oriented programming keyword, similar to how it's this in Java and C++. And I'm basically recursively calling it for every cell in the input board in this nested loop. And for my parameters of the backtracking function, I'm going to take in, of course, the board, basically the input board that I'm getting, an MIN grid. I'm going to also get the word, basically the word input. I'm going to get the row and column, basically the current cell or indice that I'm looking at in this iteration of my board search. And then finally, I'm going to get an index. But in this case, when I'm actually calling this backtracking function, instead of just passing in 0 for the index, I want to actually, instead of just passing in an index for the index, I'm going to actually pass in a 0 as basically the starting value of the first, or the 0th indice for the word. So to basically recap what this code does is for each cell, we'll call that backtracking function, and the parameters are going to be the board, basically the grid of the characters of the input, the word, basically another parameter that we're actually searching for, the row and column, the current position or index or cell value of the current position of our board, and finally 0, basically the index of the first character in the word, and that's going to be basically our index variable name. And if the backtrack function returns true for that cell, it means that we've basically found the word, and we can return true immediately. So if this actually yields to be true, in this conditional here, I'll simply return true. I don't know why that wasn't capitalized, sorry. Keep in mind in Python, you actually have to capitalize the true and false Boolean keywords, and they're not just uncapped. And once we've actually done this, now we actually have to immediately return false after exiting this nested loop if for any cell present in this nested loop for the input board, if we don't actually return true for the backtracking recursive call of the function for any cell value in this input board, that means, essentially what that's saying is that means that we've checked all the cells and none of them actually led to a successful match, and we'd return false, meaning that the word is not found in the board. Once we've actually done this, I want to actually, of course, define my backtracking function, right? Because I want to actually have something to call on line 6. So I'm gonna define backtrack, and like I talked about before on line 6, my parameters are of course going to be first self, the basically object-oriented programming keyword in Python, like I talked about like 2 times already in this video, right? It's going to be self. To actually use that self keyword to recursively call it back on line 6, that's not going to be possible if I don't actually have self as a keyword or a parameter in this case in this function. And for my other parameters, of course, I'm going to have the board. I am going to have the word itself. I'm going to have the row and column. And finally, I'm going to have my index, right? In this case, we pass in 0 to be my index when I'm actually calling the function. But of course, when I'm defining my backtracking function, I don't want to actually pass in any numerical values just yet. I want to simply have placeholder variable names that I can actually pass in values for when I recursively call the function on line 6 within the nested loop to actually iterate and call that backtracking function for every cell present in our input board. So now that I've actually defined my backtracking function, now I actually have to have my base case like I do for all backtracking functions and algorithms. It's always best practice and very important that you have your base case appear first in the function. In this case, my base case is going to be that if my index eventually reaches the length of the word, I can return true. And what this is saying is that for the base case, if index equals length of the word, if the index equals the length of the word, it means that we've basically matched all the characters in the word, and we can return true. We found a valid path or search path to actually make sure or ensure that the word is present in our input board. That's our base case. And now that I've actually checked that, I want to basically have a boundary check conditional. And so my boundary check is going to be pretty long, pretty lengthy of a conditional, but it's basically going to be like so. I'm going to have if the row is less than 0, or basically the cell value, if it's actually less than 0, or the row indice is greater than or equal to the self.rows, or the number of rows present in my input board as I stored back on line 3. Or, with similar logic, the column is less than 0, or the column is greater than or equal to the number of columns in my input board, or finally, if board at index row at index column, if that's not actually equal to word at that corresponding index, this means I am in a faltered or incorrect path of my current search to find the word, and I can immediately return false. And again, what this is saying is that it's basically the boundary check to monitor if my current row and cell indices or cell values, if it's actually out of bounds or not, or if the character in the current cell simply doesn't match the character in the word.position index. If that's actually true, we can immediately return false. Now, once I've actually completed that long conditional, now I want to actually get my temporary variable and store it in that index board, or cell value rather, row at column. Basically, temporary equals board at index row at index column. And now I can simply reset the board at index row at index column to be whatever placeholder I'd like. In this case, I'm going to just call it, let's just call it a hashtag in this case. It doesn't really matter what my filler or placeholder value really is. But essentially what this does is we'll basically store the current character at index or cell value row column in a temporary variable that we call temp. And we'll mark the current cell or value in that cell as visited by replacing the character with, in this case, a hashtag symbol or string. And essentially what this does is it prevents us from revisiting the same cell later on during this search. Now what we want to actually do is we want to basically have our for loop to actually iterate through the row and column offsets of the 4 directionally adjacent cells from our current cell, row and column. So the way we'll do this is we'll say for, I'll just call it literally just row offset, and column is set basically pair iterators. And the reason why I have pair iterators is because I'm going to actually have a loop through an array with nested tuples of length 2, so I can actually correspond one iterator with one value. And in Python, we'll say for row offset, row column offset, and basically an array of nested tuples that actually contain all the different values or cell values of the different 4 directionally adjacent cells that we can actually go to. In this case, that's going to be 0, 1. That's going to be 1. Okay, that's going to be 1, 0. That's going to be 0, -1. And finally, that's going to be -1, 0. And now, if we actually recursively call this backtracking function for these row and column offset cell values, so if self.backtrack at these new cells, actually, for our parameters are going to be board. If that actually returns true, our parameter is going to be board, word. And instead of just row and column, we actually have to do row plus row offset for the new 4 directionally adjacent cell, and column, of course, plus column offset, which are basically our 2 iterators on line 18. And finally, of course, for our index, we want to actually increment it by 1. So we'll say index plus 1. If that actually returns to be true, we can return true. So yeah, some pretty lengthy conditionals and loops here. So to kind of just make this a little bit more simpler, we'll basically explore all the different 4 possible directions from the current cell, or basically all the 4 different directionally adjacent cells of this current cell at index row, index column. And we'll do this by adding the offsets to the row and column. Then we'll recursively call the backtracking function on the new position with index plus 1, basically incrementing our index by 1 to check the next character in the word. And if any recursive call returns true, we can return true immediately. Of course, once we've actually done that, we can reset. Once we actually exit this for loop, we can reset our board at index row, at index column, or basically the cell value in this case, from our hashtag back to our temporary variable. And that's literally just the entire use case of the temporary variable, to actually just temporarily store every single cell value for board at index row or cell value row column. And once I've done that, I can return false, otherwise if this doesn't actually return true. And essentially what this does is if no match is found in any direction for any cell, we can return false to indicate that the word cannot be constructed from the current cell, and we actually have to move on to another non-invalid or valid search from a different cell value, right? And on line 21, what we do is we'll basically If none of the directions actually led to a solution, we can basically backtrack by resetting the current cell to its original character stored in the temporary variable, and we can move on to the next iteration, or basically next search path, and set board at index row at index column back to its temporary or original value, so we can actually potentially use it on in our next path. And now this should be completely fine. This should be submitted, and unless I made any syntax errors here. Oh yeah, okay. I know what I did wrong. This should be board, not grid. Sorry about that. But yeah, now this should be fine. This should be accepted. It's just judging. Give it some time. And as you can see, it's just about as efficient as you can get. So to basically just give an overall explanation of, again, what this code actually does is this algorithm basically uses backtracking, or the backtracking algorithm, to explore the grid, where we start from each cell and try to match the word character by character. And if you reach a dead end, either by going out of bounds or not matching the current character with its corresponding word at that corresponding index, we'll backtrack by resetting the state of the board and continue on exploring from a different direction until we actually hit that base case of basically when the index equals the length of the word, meaning we've actually found the word to be present within our input board, and we can return true. So for the time and space complexity for this algorithm, the time complexity is going to be big O of n times 3 to the power of L, where n is the number of cells on the board and L is the length of the word. And we basically have n starting points for each cell. And from each cell, we can move up to 3 valid directions, since one direction is, of course, where we came from, repeating this L times, right? That's the reason why it's big O of n times 3 to the power of L. And space complexity-wise, this is going to be big O of L, right? Because the recursion depth can go up to the length of the word L. So yeah, if you guys enjoyed this video and learned something new, please consider liking this video and subscribing to my channel. It really does mean a lot. And without further ado, I will see you guys in the next video. Bye-bye.